The most characteristic property of carboxylic acids is the one that gives them their name, acidity. Just like alcohols, carboxylic acids react with electropositive metals like sodium and liberate hydrogen gas. Unlike phenols, carboxylic acids react even with weaker bases, such as carbonates and bicarbonates, to form the corresponding salts with the evolution of carbon dioxide. The reaction of carboxylic acids with weak bases clearly proves that they are tremendously more acidic than the very weak organic acids, alcohols and acetylene. Hence, the reaction of carboxylic acids with carbonates and bicarbonates is used to detect the presence of the carboxyl group in an organic compound. Carboxylic acids are much stronger acids than water. In an aqueous solution, a carboxylic acid exists in equilibrium with the carboxylate anion and the hydronium ion, as shown in the equation here. As for any equilibrium, the concentrations of the components are related by the expression Keq is equal to the product of the concentrations of RCOO- and H3O+, divided by the product of the concentrations of H2O and RCOOH. Since the concentration of water remains almost constant, we can combine it with Keq to obtain the expression Ka is equal to Keq multiplied by the concentration of H2O is equal to the product of the concentrations of RCOO- and H3O+, divided by the concentration of RCOOH. Here, Keq is the equilibrium constant, and Ka, which is equal to Keq multiplied by the concentration of H2O, is called the acid dissociation constant. Every carboxylic acid has its characteristic Ka, which indicates how strong an acid is. The larger the value of Ka, the greater is the extent of ionization, and therefore, the stronger is the acid. For example, among the unsubstituted monocarboxylic acids, formic acid with the highest value of Ka is the strongest. The values of Ka are usually very small. Hence, for convenience, they are often quoted in logarithmic form as pKa is equal to negative log Ka. Most pKa values fall within the range of 1 to 14. The smaller the pKa, the stronger is the acid. For example, among trifluoroacetic acid with a pKa value of 0.23, benzoic acid with a pKa value of 4.19, and acetic acid with a pKa value of 4.76. Trifluoroacetic acid with the lowest pKa value is the strongest organic acid. Stronger acids have pKa values less than 1. For example, trifluoroacetic acid with a pKa value of 0.23 and trichloroacetic acid with a pKa value of 0.65 are strong acids. Acids with pKa values between 1 and 5 are considered moderately strong. For example, fluoroacetic acid with a pKa value of 2.66, chloroacetic acid with a pKa value of 2.86 and nitroacetic acid with pKa value of 1.68 are moderately acidic acids. Weak acids have pKa values between 5 and 15. For example, phenol with a pKa value of 9.95, orthocresol and with a pKa value of 10.28 are weak acids. Extremely weak acids have pKa values greater than 15. For example, ethanol with a pKa value of 16.0 and acetylene with a pKa value of 23.0 are extremely weak acids. Carboxylic acids are acidic and readily lose a proton because the carboxylate ion formed by ionization or reaction with a base is stabilized by resonance. According to the resonance theory, the carboxylate ion is a hybrid of two structures, which, being of equal stability, contribute equally. The negative charge is evenly distributed over the two oxygen atoms. Let's now compare the acidity of carboxylic acids with the acidity of phenol. When you compare the resonance structures of the carboxylate ion and the phenoxide ion, you can clearly see that the carboxylate ion is stabilized by two equivalent resonance structures in which the negative charge is on the more electronegative oxygen atom. The phenoxide ion, on the other hand, has non-equivalent resonance structures in which the negative charge is on the less electronegative carbon atom. Hence, resonance is more important in the carboxylate ion than in the phenoxide ion. Furthermore, the carboxylate ion is more resonance stabilized than is the phenoxide ion. This is because a negative charge is more effectively dispersed over two electronegative oxygen atoms in carboxylate ions, less so over one oxygen atom, and the less electronegative carbon atoms is phenoxide. Thus, carboxylic acids are more acidic than phenols. Let us now examine the effect of substituents on the acidity of carboxylic acids. Electron withdrawing groups increase the acidity of carboxylic acids by stabilizing the anion through the dispersal of the negative charge on the carboxylate ion by the inductive or resonance effects. For example, chloroacetic acid with the electron withdrawing chlorine group is 100 times as strong as acetic acid. The acidity of carboxylic acids increases with an increase in the number of electron withdrawing groups. For example, trichloroacetic acid with 3 electron withdrawing groups is more acidic than dichloroacetic acid with 2 electron withdrawing groups, which in turn is more acidic than monochloroacetic acid with 1 electron withdrawing group. The strength of the electron withdrawing substituent determines the magnitude of the effect on acidity. For example, fluoroacetic acid is stronger than chloroacetic acid, which in turn is stronger than bromo and iodoacetic acid. This is in accordance with the decrease in the electronegativities of halogen atoms. The nearer the electron withdrawing group, the greater is the acidity of carboxylic acid. For example, Among the halo-substituted acids shown here, alpha-chlorobutyric acid with the chlorine atom on the alpha carbon is more acidic than beta, which, in turn, is more acidic than gamma-chlorobutyric acid. The increasing order of acidity of some of the electron-withdrawing groups is as shown here. Note that, in the case of carboxylic acids, in which the phenyl or vinyl group is directly attached to the carboxyl group, there is an increase in the acidity of carboxylic acid instead of the decrease expected due to the resonance. This is because of the fact that the carboxyl group is attached to a more electronegative sp2 hybridized carbon. Electron-donating groups, on the other hand, decrease the acidity by destabilizing the anion by intensifying the negative charge. Thus, among the unsubstituted aliphatic monocarboxylic acids, formic acid, with no alkyl group, is about 10 times stronger than acetic acid, which in turn is stronger than propionic acid, and so on. In the aromatic carboxylic acids too, electron-withdrawing groups increase the acidity, while electron-donating groups decrease it. For example, para-nitrobenzoic acid with an electron-withdrawing group is more acidic than benzoic acid, which in turn is more acidic than para-methoxybenzoic acid with an electron-donating group.